Okay, so finally coming to the towards the end of chapter 2 here. Um, so here are the current assignments, and these are all the assignments for the material that's up to what's going to be on exam 2. So I'll have an assignment posted for section 2.8 after class, and excuse me, send you the link in the usual email I usually send to you. Um, that's going to be due on Monday. The final web assignment due on Monday, and the exam will be on Tuesday, covering 1.6. Excuse me, 1.6 to 1.8, 2.1 to 2.8. So then after that, there's 10 sections left. So looks like we're right on schedule. I know some of you have said to me it feels like we're going really fast. Again, the class is compressed time wise because it's a summer class, 1 week fewer than what we normally have. No final exam period, and we do have to cover everything on the syllabus. So that's just the way the course is designed. Um, so again, if you need help, just come to me and we'll see what we can do. Um, all right. So section 2.6, let's do a few problems in there. So what was assigned was 9 through 69, every third problem. So this notion of shifting graphs is nice, and it actually gives you a complete way of graphing some types of functions, for example, quadratic functions. Let's look at 45. So in number 45, so sketch the graph of the function given, using these transformations and, starting with a standard graph and then using transformations. So this one is y equals x minus 3 squared plus 5. All right, so if we start with, the standard function that is the just ordinary parabola, y equals x squared, right? This function, right, is obtained from this by shifting up 5 units and shifting right 3 units, right? Because this is of the form y equals x minus 3 squared plus 5 is of the form y equals f x minus 3 plus 5 for f of x equals x squared. So 3 is subtracted from x, and then 5 is added to the whole function. So starting with the standard parabola, you can never draw it all in one go to make it symmetric looking. All right, close enough for now. No, it's still ugly. So there's the parabola. So we've got the standard parabola in the xy plane. So here's the x-axis, y-axis. So now all we're going to do is shift it up 5 units and shift it right 3 units. So make it a different color as well. So we're going to go up 5. Now, again, you don't have to be so precise about where you, about the scale on your x and the y axis. So here's up 5. We'll just say right here, and then over 3, right about there. Maybe right here. And you just label it as such. Or no, that definitely is not it, because it is... needs to be... yeah, maybe here. Let's see. So the black graph is y equals x squared, and the red graph is y equals x minus 3 squared plus 5. And so, because this is the point 0, 0 down here at the origin, this is the point right here, right 3, up 5. So, it's the same graph, just shifted accordingly. So, how can this idea tell us how to graph any quadratic function? So this trick works for graphing any quadratic function y equals ax squared plus bx plus c. So forgetting about the a for the moment, let's just assume a is equal to 1. But this trick works for graphing any quadratic function after, right, because all these shifts can be applied after completing the square. Now, completing the square here, this is not part of the problem, but just some extra information. Completing the square here is a little bit different. Okay, we don't have an equation here. Yeah, I know it's an equal sign with a quantity on the left and a quantity on the right. Well, an expression on the left and an expression on the right. Yes, in that sense, it's an equation, but it isn't really, because here we're saying the left-hand side is just the name of the function, so to speak. So, function y is this, right? So you can't really add something to the other side. If you do, you have to subtract it and put it back over here. So, there is that extra little bit that goes along with completing the square. But let's just do a little example of what I'm talking about. So let's sketch the graph of y equals x squared plus 5x minus 3. Okay. This one doesn't factor, by the way, but that doesn't matter here. Okay, so we want to sketch the graph of x squared plus 5x minus 3. So first thing we want to do is complete the square. Okay, so, well, let me make an even number here. So, x squared plus 6x plus 3. So first thing we want to do is complete the square. 6 over 2 is 3. Square it, you get 9. So you want to add the 9 to both sides. Okay, but you can't leave this 9 over here. You have to bring it back over there. Okay, so y is equal to x squared plus 6x minus 3 plus 9 minus 9. You have to have just y on the left. So there's that extra little step that you have to do when completing the square. You can sort of go from here to here instead. Rather than adding 9 to each side, what you do is you add 0 to the right. Right? Anytime you change the quantity on the left, you must change the quantity on the right by the appropriate amount, or vice versa. Right? But I'm not changing the quantity on the right, I'm just adding 0 to it. But I add 0 in this clever way, 9 minus 9. Where to get the 9 from? Well, the 9 is 6 over 2, which is 3 squared. Okay, so you can just go from here to here like that. Actually, we're going to do a section on this later, I believe. Yeah, I think 3.1 is on this exact thing. Quadratic functions. Yeah. But, it's a nice example, so we'll do it. So bring the 9 over here, because that's the nice number that you want. In order to complete the square, then minus 3 minus 9 is minus 12. So this is y equals x plus 3 squared minus 12. Boom. Right, so this is obtained from y equals x squared by shifting down 12 units and left 3 units. See? So once you complete the square, it puts the quadratic function, any quadratic function, into this format, which tells you, well, that's how you graph the thing. Right? Starting with y equals x squared and then applying some shifting. Now, there could be an a involved in there, like the coefficient of the x squared may not be 1, in which case there may be an a in here, which is going to involve some flipping and stretching and things like that. But we'll cover that in section 3.1. But it's still the same idea. Same idea. All right. So what else in 2.6? So every third problem. So I assigned to you numbers 46 and 50. So 50 uses an absolute value expression. Let's take a look at something that also does use absolute value. 31. So in 31, you got absolute value x minus 1. So this is like number 50. So sketch the graph of y equals absolute x minus 1. Okay. First of all, the standard function in mind here is y equals the absolute value of x. First, y equals absolute value of x is equal to what? Well, how's that absolute value function defined? It's a piecewise function. And what's that piecewise function look like? Oh, I hate to bring it up again, but oh man, that piecewise function business that we did in section sketching the graph of a function. I think it was in 2.2. In 2.2, yeah. So in section 2.2, we talked about sketching the graph of a function, and one of the homework problems was, sketching the graph of a piecewise function, where each piece was a line of some sort. Man, it just, the results on that weren't good. You really got to look at that, guys. Okay, we need to understand piecewise functions. They're kind of funny when you look at them at first, but they come up in a variety of situations. So it's something we definitely want to understand. Okay, so spend a little extra time with that. You want some help? Just come and ask me, or go back and review the examples we did. We did plenty of examples in section 2.2. Right, so go back to the video lecture on 2.2 and go back to the day we discussed problems in section 2.2. All right. So the absolute value of x is actually defined as a piecewise function. It's equal to x if x is bigger than or equal to 0. If it's already positive, the absolute value of x is just x. If x is negative, actually I should do these the other way around. So x if x is bigger than or equal to 0. What if x is less than 0? Then absolute value of x is equal to what? All right, the absolute value of negative 3 is what?
3.
3, right? So, how do you get that? Well, you erase the negative 3, the negative. Well, okay, yes, but that's not like an algebraic thing, right? That's
because it's 3 away from 0.
Yeah, that's like a geometric idea. How algebraically do we transform negative 3 to 3? What's the algebraic way to get from negative 3 to 3?
Is it plus or minus 3?
Well, what can I do to a negative to make it positive algebraically? I can multiply by negative again, right? So, yeah, it's 3, but think of it this way instead. Right? So if x is negative, then the absolute value of x is negative x. If x is less than 0. Right? X is already negative, so when I stick a negative in front of it, it becomes positive. Right? So now, right, we have these two lines. So this is the line of slope negative 1. This is the line of slope 1. Right? So y equals x is this line. Y equals negative x is this line. Okay, but we want the line y equals negative x for negative values of x, and y equals x for positive values of x. So it looks like this. So the switch happens at x equal to 0. At x equal to 0, these quantities are both 0. And then for x is bigger than 0, we have the line y equals x, which is the line of slope 45 degrees emanating from the origin. And then for x's that are negative, we have the line y equals negative x, which is the line of slope negative 1, whose y-intercept is at 0. So this is the graph y equals absolute value of x. Looks like that. Standard graph, right? So this is the standard graph. In this case. Right? So in number 31, So y equals absolute value of x minus 1 is obtained from y equals absolute x by doing what? Just so the standard function f of x is just absolute value of x. So I'm subtracting 1 from the absolute value of x. So I go from absolute x to absolute x minus 1 by doing what geometrically? By shifting how? Down 1 unit. So we've got this graph. Y equals absolute value of x minus 1. So here's a little extra. Sketch the graph of y equals 1 minus absolute value of x. So instead of, absolute x minus 1, I've got 1 minus absolute x. What's the relationship, again, between a minus b and b minus a? How are they related to each other?
They have the same absolute value.
Mm-hmm. Right. So how do you get from one to the other in that case? Like 3 minus 5 is 2. Or sorry, 5 minus 3 is 2, and 3 minus 5 is negative 2. So the relationship is what?
Commutative property?
Not commutative, actually, right? Because a minus b is not b minus a. A minus b is the negative of b minus a. A minus b is the negative of b minus a. So here, right, absolute x, 1 minus absolute x is the negative of absolute x minus 1. Okay. So y equals 1 minus absolute x is equal to the negative of absolute x minus 1. Right? So y equals the negative of absolute x minus 1 is obtained from y equals absolute x minus 1 by negating the whole function. So when you negate the whole function, this function, geometrically, it does what? When you negate the whole function. Right? When you negate the y values, it takes the graph and does what to it? It reflects it how? We're reflecting about the x-axis. So this is y equals absolute x minus 1. So if I take that graph and I reflect it around the x-axis, then I get the graph that we're looking for. So this is, so that's negative 1 here, this is positive 1 here. this is the graph y equals 1 minus absolute x. Right, I just flipped it, right, which is equal to the negative of absolute x minus 1. Just flipped it around the x-axis. How about, so I'll give you 46 and 50. So 46, we had one like that during class. How about, how about 48? So sketch the graph of um, 2 minus absolute x, or square root x plus 1. So a couple ways you can arrive at this. You can do this negating thing. So the standard function we want to start with, right, is definitely going to be square root of x. Y equals square root of x. Is y equals root x. So y equals square root x. It's like a parabola. Okay, but only half of it because you're only using positive arguments underneath, and the answer is always positive. Okay, so y equals square root x. So how can we arrive at this? Okay, so let's do something a little bit different than we did in the last problem. So I can apply what transformations here? Well, y equals 2 minus square root x plus 1. So I'm not going to negate it this time and flip it around. I'm just going to write it like this. Negative square root x plus 1 plus 2. So I'm going to start with y equals square root x. Right? With y equals square root x, I will reflect around the x-axis. That'll be step 1. Reflect around x-axis. Reflect around the x-axis, and you get this. Just negating the whole function. All right, so this is f of x is equal to square root x. So to reflect around the x-axis, you just negate the whole thing. And now I'm going to shift up 2 units. All right, so this is y equals minus fx plus 2. So that's minus square root x plus 2. And then shift left 1 unit. So y equals minus fx plus 1 plus 2. So that's minus square root x plus 1 plus 2. So then I get to the function that I want to graph. Minus square root x plus 1 plus 2. So you start with square root x, negate it, add 2 to the whole function, and then add 1 to the argument of the function. So here's the graph. stop. Okay, so here is y equals square root x. Guess I need a full set of x and y axes here. I'm actually gonna. All right. So first we're gonna reflect around the y-axis or x-axis. So that's going to flip this guy upside down. All right, and then we're going to shift 2 units up. So 1, 2, and then shift left 1 unit. So looking something like that. And you indicate that shift by, specifying what this point is. So that was the point 0, 0, right? And then you go up 2, left 1, so that's the point -1, 2. This is the point 0, 0. And so this is that function that we want. Y equals minus root x plus 1 plus 2. Okay. So number 46 is a lot like that, although there's no reflecting involved. It's just shifting. All right. Let's see, any other interesting problems here? So by the way, so far in this section, we have looked at a few more graphs of functions and sort of made them standard in our minds. Okay, so we've got lines. Lines, we know all about lines. We've talked about lines. And we also know about parabolas now, and we really know how to graph parabolas or quadratic functions. So linear functions and quadratic functions, we're kind of okay with that now. And then, we also introduced this absolute value x function. Right? That's an important one too. So y equals the absolute value of x, and y equals square root of x. We've been talking about that one. So we've got this catalog of functions that we kind of know what their graphs look like or have a decent idea. And later on we'll even go with a few more. So alrighty. It gets you away from, just plugging it into the calculator and then looking at this picture, but kind of not really knowing as much about the picture as you should. All right, so the next section, section 2.7, is on combining functions. So given two functions f of x and g of x, right, whose ranges are the real numbers, if the ranges are not the set of real numbers, then you can't necessarily do this. We can add, subtract, and multiply, divide these functions as follows. Okay, the function f plus g, right, is defined as f plus g of x is just simply defined as fx plus gx. And because f of x is a real number and g of x is a real number, you can define it like that, no problem. You can also subtract them. Right? By the way, these are definitions. Okay, this isn't algebra, these are definitions. So the definition of the function f plus g is f of x plus g of x. It's not multiplication here. This is just the way functions are defined. I'm not like distributing this x over the f and g or something like that. F times g of x is equal to fx times gx. You're just multiplying two functions together. And then f over g of x is equal to fx divided by g of x. Right, so, whatever you do with real numbers, you multiply, divide, add, and subtract. You also can do exponents, although we're not going to discuss it here. You can do with functions that have real values. So, for example, given fx equal to, here's my example, 2 over x plus 1, and gx equal to x over x plus 1, we get that f plus g of x is equal to, well, it's fx plus gx is 2 over x plus 1 plus x over x plus 1, which is 2 plus x over x plus 1. F minus g of x is fx minus gx. 2 over x plus 1 minus x over x plus 1, which is 2 minus x over x plus 1. And then f times g of x is fx times gx, the product of the two functions. 2 over x plus 1 times x over x plus 1 is 2x over x plus 1 squared. And f over g is fx divided by gx is 2 over x plus 1 over x over x plus 1, which is equal to 2 over x plus 1, x plus 1 over x, right? Multiplying by the reciprocal is just 2 over x now, right? So adding, subtracting, and all, that kind of stuff you can do with functions whose ranges are real, in the real numbers. In other words, real number valued functions. So that's one way of combining functions, but the most important way that comes up the most is called composition of functions. Given two functions and g of x whose domains and ranges are within the real numbers, real numbers, we define the composition so it's f and then this little circle g of x. We define the composition, this, called f, and you say following g of x. So that little circle is called following. F following g of x is defined like this. We define the composition called that as shown. So f following g of x is f of g of x. So the argument for f becomes g. So it kind of looks like this. So here are the real numbers. And there's the real numbers. And here's the real numbers again. If you have an x right here, first applied to x is g. So this is x, and then this is g of x within the real numbers. And then following, right, so f following g, following means that f comes after g, right? F following g. F is following g, right? From left to right, f is first and g is second. But in terms of functions, g is applied first because it's evaluated inside out. So g comes first, then f. So we take x, we apply g to it, and then we apply f to g of x like this. So this right here is f applied to g of x, which is f following g of x by definition. Okay? Not g of x, this is g, this is f. So f following g. But, we write it in reverse notation like that so that this looks like that. So as not to confuse the notation. So f following g. So following means come after. So let's look at these two functions again and look at the various compositions that you can get of those functions. Here they are. So given fx and gx, okay, evaluate, so find the expressions, find the simplified algebraic expressions for, so we'll do f following g, we'll also do g following f. We'll also do g following g, and we'll also do f following f. So You can, compose functions however you want. You can compose a function with itself. You can do f following g, and you can do g following f. By the way, they're not the same thing, right? So it's another one of these non-commutative operations, right? Like, not multiplication, subtraction, right? Subtraction is not commutative. 5 minus 3 is 2. 3 minus 5 is negative 2. It's not commutative, but it's kind of almost commutative because, a minus b and b minus a are very closely related. Here, f following g and g following f have absolutely no relationship whatsoever, but let's check it out. So, f following g of x. So, by definition, this is f of g of x. So, let's evaluate inside out. What is g of x? It's x over x plus 1. What is f of x? It's 2 over x plus, you know what, I don't want to have both with x plus 1. That might be confusing. Let's do 2x minus 1. How about that? Yeah, that'll be a little better, I think. Okay, so g of x is x over x plus 1. So f, and let me, that's fine. Right, so I have 2 over 2x minus 1. That's f. It's 2 over 2 blank minus 1. Right, f of x is 2 over 2 blank minus 1. So what goes in the blank here if I want f of x over x plus 1? What goes here? Right, f of x is 2 over 2x minus 1. So f of z is 2 over 2z minus 1. So f of 3 is 2 over 2 times 3 minus 1. Now, you don't have to stick in just a symbol. So f of, say, x minus 1 is equal to what? 2 over 2 times what? Minus 1.
X minus 1.
Yeah. What goes in the blank is right here. Right? F of x, 2 over 2x minus 1. So whatever I put in here, I replace every instance of x with that thing that's in the parentheses there. So here, I replaced x with z. So the instance of x that was here gets replaced by z. Here I replaced x with 3. So the instance of what I replaced x was, so the instance of x here gets replaced by 3. Here I have x minus 1. So the instance of x gets replaced with x minus 1. Not forgetting the parentheses. Now I could put x plus 1, in which case it would look like that. I could put x plus 6, in which case it would look like that. Or I could put x over x plus 1. Like that. Right? Every instance of x in that gets replaced with x over x minus 1, or x over x plus 1. Right? So instead of 2 over 2x minus 1, I have 2 over 2 times whatever this thing is, minus 1. So now I've evaluated what this thing is algebraically. Now I just want to simplify it. So a nested fraction expression. So this is 2 over 2x over x plus 1 minus x plus 1 over x plus 1. So that's 2 over 2x minus x minus 1. Like that. So this is equal to 2 over 1 times x plus 1 over x minus 1. Take the top fraction and multiply by the reciprocal at the bottom. So that's 2x plus 2 over x minus 1. There's my simplified expression for f following g of x. How about this? G following f of x. Right, this is g of f of x. What is f of x? F of x is right here. F of x is 2 over 2x minus 1. So now what is g? So let's write g. Instead of with x in it, I'm just going to put a blank. So blank over blank plus 1. Right, so g of x where'd it go? G of x is equal to x over x plus 1. So I have two instances of x. So g of blank is blank over blank plus 1. So what goes in the blank is whatever I've got here. So that's 2 over 2x minus 1. 2 over 2x minus 1. So that is the composition g of f of x, or g following f of x. Okay, now we want to simplify this expression. So here I have 2 over 2x minus 1 plus 2x minus 1 over 2x minus 1. So adding the fractions in the bottom here, I have, so this is 2x plus 1. Multiplying the top fraction times the reciprocal of the bottom fraction. Those cancel, and I get 2 over 2x plus 1. Notice they're not the same. F following g is not g following f. I mean, in rare instances, they might be. Very rare instances, but in general, they're just not the same thing. I mean, as you can see, they're quite different here. All right. So that was f following g and g following f. We could also do f following f. So what was f of x again? F of x was 2 over 2x plus 1 or minus 1? 2x minus 1. Okay. So now f following f of x is f of x. Is f of, well, what's f of x? It's 2 over 2x minus 1. So I need f of this thing here. So that's 2 over 2 times blank minus 1. What goes in the blank right there? Just take this, put that there. So that's 2 over 2x minus 1. And then simplify. So 4 over 2x minus 1 minus 2x minus 1 over 2x minus 1. So this is equal to, so 4 minus 2x minus 1. All right, remember when you subtract the fraction, you have to subtract the numerators. So it's 4 minus the whole of 2x minus 1. So I need that parentheses there. So that becomes plus 1. So 5 minus 2x. So in the end, this becomes so 4x minus 2 over 5 minus 2x. So that's f following f. You could also do g following g. So this, ooh, did I ever start that? I did. Okay, good. G following g, what was g of x? It was x over x plus 1. So g following g of x is g of x. So g of x is x over x plus 1. So g of this, well, again, it's blank over blank plus 1. What goes in the blank is this expression. Every instance of x gets replaced with, whatever was in that expression there, the argument of g, it's called. Like that. All right, so this becomes x over x plus 1 over, so this becomes x over x plus 1 plus x plus 1 over x plus 1. So that's 2x plus 1 over x plus 1. So then actually these guys cancel and you get x over 2x plus 1. Did a little shortcut there. That's okay. If you don't like the shortcut, you could always just, go the long way around. All right, so with two functions, that would be the 4 ways to combine them using this operation, this composition operation. So the operation is called composition, but when you say the operation, it's uses the word following. Okay, but you call it the composition. So G following G is the composition of G in itself, or G following F is the composition of G then F. Right? Same way you say like 3 times 5 is the product of 3 and 5. So composition is the result. Following is the operation. So 5 is the sum of 2 and 3. 5 is the sum, 2 plus 3. The result is the sum. The operation is plus. Let's look at one more example. So let's take one from the book. 57, 58. Like number 51. So we've got f of x is 1 over x. G of x is equal to 2x minus 1. No, 2x plus 4. All right, find F following F, G following G, F following G, G following F. Okay, well, this one's going to be a lot easier than the one we just did because there's no algebra really to do afterwards, but F following G of X is F of G of X. Now, by the way, you don't have to evaluate the thing inside first. You can evaluate the thing on the outside first. All right, so F of X is 1 over X. So F of G is 1 over G. All right, F of X is 1 over X, so F of G is 1 over G. And then 1 over G is, and then G of X is just 2X plus 4. So that's F following G. G following F of X. That's G of F of X. Well, G of X is 2X plus 4. So G of F is 2F plus 4. So that's evaluating the outside first and then the inside afterwards. And then F of X is 1 over X. So this is 2 over X plus 4X over X. So that's 4X plus 2 over 2X plus 4. So not the same, right? So F following G, G following F, not the same. They're very different, in fact. There's really no relationship at all between them. F following F of X. So that's F of X, right? F of X is 1 over X, so F of F is 1 over F. And then F of X is 1 over X. So that's just X. And then G of G, G following G, is G of X. So G is, so let's do inside out this time. I like inside out more than outside in. Whichever way, makes more sense to you, doesn't matter. So this is G of 2X plus 4, because G of X is 2X plus 4. So now G is 2 of blank plus 4. What goes in the blank is this, 2X plus 4. So this becomes 4X plus 8 plus 4, which is 12. All right. So that's everything in this section. One more section to go, which we'll cover tomorrow, and then maybe we could have a little bit of review time before the exam on Tuesday this time around. All right, so that's all for today. I have open office hours at 11:30 in my WebEx room. I'll send the link with the email after class. Okay, so have a good afternoon, everybody, and I'll see you next time.